There's a star in our galaxy that refuses to behave. It doesn't shine the brightest or burn the hottest, but NASA has to watch it 24/7. Its name is PSR J09520607. A sphere smaller than a city, yet heavier than 2 suns. A teaspoon of its matter would outweigh a mountain. And deep inside, atoms no longer act like atoms. They've been pressed into something stranger, the ghost of matter itself. This object isn't stable. It's balanced on the edge, one wrong turn, a breath more mass, and it collapses into something far darker. A black hole born without light, without sound. It's not far away either. 14,000 light years close by cosmic standards. A ticking pulse right here in our own Milky Way. Tonight we travel to the endless space and get to know everything about this dangerous star. We stand on the edge of a dying star. It burns not with colour, but with resistance, a final battle against its own gravity. Imagine the surface trembling layers folding inward, the heart of the star collapsing under a weight it can no longer carry. For millions of years it held the balance fusion pushing outward, gravity pulling in. But when the fuel ends, gravity wins, and what follows is not destruction, it is transformation. The core implodes, shrinking from a sphere the size of our sun into something no wider than a city barely 20 kilometers across. If you could drive from one end to the other, you'd reach the edge before a single song finished playing. Yet in that small space lies more mass than the entire solar system. Every mountain, every ocean, every planet you know could be crushed into that single sphere, and still there would be room left inside. The moment of collapse is violent beyond comprehension. Temperatures soar above 100 billion degrees. Atomic nuclei, the very building blocks of matter, break down. Protons and electrons merge into neutrons. The light goes out and a new object is born, a neutron star. Dense, dark and silent. Not dead, just different. You can picture it now, an invisible weight in space no larger than Manhattan, yet so heavy that a teaspoon of its material would weigh over 1 billion tons. Imagine holding that spoon. Your arm would sink through the planet, tearing through rock and mantle until it reached the Earth's core without slowing. The fabric of matter itself cannot resist such compression. We call this state degeneracy pressure, a kind of invisible scaffolding built by quantum mechanics. It's what keeps the neutrons from collapsing further. But even this law of physics has limits. Add too much mass and not even quantum rules can stop gravity from winning again. That is how a neutron star can die a second death when it crosses an invisible line and becomes a black hole. Now close your eyes for a moment. Picture standing beside this remnant, a sphere so compact that if it replaced our sun, Earth would orbit it once every few seconds. The daylight would vanish. The sky would curve around its gravity. Your heartbeat would sync with the pulse of something that should not exist yet does. Think of the silence. No sound travels here. Only the faint whisper of magnetic storms, the echo of the explosion that made it. Around us float the remnants of that lost sun, glowing filaments of gas expanding outward for thousands of light years like petals from a shattered flower. Some of those fragments will one day cool and drift together, creating new stars. Others will circle back, feeding the remnant, forcing it to spin faster, heavier, closer to collapse. And this is where our journey begins, standing between survival and surrender, between what physics allows and what the universe demands. We move closer now into the gravity well itself. You can almost feel it tugging at your thoughts, bending them toward its center. The neutron star no longer shines. It simply is a piece of matter so condensed that light barely escapes the curvature surrounding it. This is density beyond comparison, where the idea of solid or liquid becomes meaningless. Let's give that density a shape. Take a single teaspoon of its material no larger than a sugar cube, and it would weigh more than 1 billion tons. That's roughly the mass of every skyscraper in New York City combined, pressed into a space that would vanish between your fingertips. If that teaspoon somehow appeared here on Earth, it wouldn't rest on the table. It would plunge straight through the crust, slice the mantle, and settle in the planet's core in less than a second. Now try to imagine the surface gravity. On Earth you weigh whatever your scale tells you, maybe 70 kilograms. On a neutron star you would weigh about 10 to 14 times more. A single step would crush you into atomic dust. Even an iron sphere a meter wide would collapse into a thin film of atoms the moment it touched the surface. The gravitational field is so strong that if you dropped a marble from 1 meter above the crust, it would hit the surface at nearly half the speed of light. It's hard to picture because human senses were never built for this kind of scale, so let's anchor it. If the neutron star were the size of a soccer ball, its mass would be greater than Mount Everest, no greater than Earth itself. Compress the entire planet into that size, and you would get only a fraction of its density. This is not simply a heavy object. It is a place where matter itself has lost its identity. Inside, there are no atoms, no molecules. The immense gravity crushes everything into a sea of neutrons packed so tightly, they begin to blur into one another. Quantum mechanics holds them apart, but barely. The neutrons vibrate in place, trapped by gravity's hand a trillion times denser than lead. This is matter, at its limit, the skeleton of the universe revealed. And yet, it spins. A city-sized object rotating hundreds of times each second. You can think of it as a cosmic flywheel, a relic of the dying star's rotation. As it collapsed, it conserved angular momentum, the same way an ice skater spins faster by pulling in their arms. What was once a slow rotation of days becomes a blur of milliseconds. Each turn drags magnetic fields across space, sculpting invisible arcs of radiation. Pause here. Picture standing at a safe distance, say 1,000 kilometers away, floating in the black. The star below you glows faintly blue, its magnetic field wrapping it like ribbons of fire. Space itself curves inward, a visual illusion so deep that the horizon seems to fold. You could orbit it in seconds. Time near its surface runs slower than your heartbeat. Every moment you spend here is already part of the past when measured from afar. And this is just one example in a galaxy of hundreds of millions. Most are silent, some pulse like cosmic clocks. Others drift alone, cooling for billions of years. But all share one truth: density is destiny. The universe pushes matter toward compression, toward limits, toward the edge where even light must bow. We are still here, hovering above the surface of the impossible. Beneath us, gravity is not a pull, it is a command. Every atom obeys without question. You can almost feel it, an invisible pressure tightening around your chest, a weight that doesn't just drag down but inward. Gravity here is not merely a force, it is geometry made ruthless. On Earth, gravity keeps oceans steady, moons in orbit, bodies grounded. It is gentle 1g, but on a neutron star it is 100 trillion Gs. If you could stand here, your body would flatten to a layer thinner than a strand of DNA before you even realized you had touched the ground. Space-time itself bows under this mass, curving so sharply that light bends nearly full circle before escaping. You could look forward and see the back of your own head. Let's test this in numbers. Suppose this neutron star has a radius of 20 kilometers and a mass of 2.4 times that of the Sun. Using Newton's law of gravitation, the surface gravity reaches around 2 × 10^12 s2. That's the kind of acceleration that could pull an orbiting spacecraft from 100 kilometers above down to the surface in less than a millisecond. Even the crust beneath, only a few centimeters thick, bears pressures that dwarf the atomic forces holding ordinary matter together. And yet, it does not crumble. The crust of a neutron star is thought to be the strongest material in the universe. Scientists call it nuclear pasta, a lattice of neutrons and protons bound together so tightly that 1 square meter of it could support the weight of a mountain. Its strength is 10 billion times that of steel. Imagine a single spoonful of this matter, it could prop up the entire skyline of Tokyo without bending. We used to believe there must be a limit to what matter can endure, a final point where everything breaks. But the neutron star redefines that limit. Here, electrons are crushed into protons, producing neutrons that huddle shoulder to shoulder in infinite patience. This is matter stripped of individuality, atoms replaced by a single identity mass obeying gravity. And still, there is a boundary, the Tolman-Oppenheimer-Volkoff limit, or TOV limit, around 2.5 to 3 solar masses. Cross it, and even degeneracy pressure collapses. No known law can prevent the fall. The neutron star would sink into itself, its gravity escaping all bounds, birthing a black hole. You might think of it like the tension in a rope pulled too tight. For now, the rope holds humming with strain, but every photon that leaves its surface whispers the same warning: not yet, but soon. We drift higher away from that crushing surface, watching the curve of the star fade into the velvet dark. Somewhere deep below, gravity keeps singing its low, relentless note, a reminder that even the strongest material in the cosmos still owes its life to balance. And balance in this universe never lasts forever. The silence of gravity still lingers in your ears. You remember the crushing surface, the star that bent light into a circle, the matter that refused to yield. But not every remnant of collapse stays quiet. Some learn to sing again. And now, as we drift away from that frozen mass, a new kind of pulse begins to reach us, steady, rhythmic, relentless. At first it sounds like a heartbeat. Then you realize it is not sound at all, but light flickering across the dark like a cosmic lighthouse. Each flash marks one full rotation of the neutron star we left behind, spinning hundreds of times every second. From a distance it looks calm. Up close it is a storm of radiation electrons and magnetic fury. This is what we call a pulsar, a neutron star that spins so fast it becomes a clock for the universe. As it rotates, beams of radio waves and X-rays shoot out from its magnetic poles. They sweep through space like the beams of a lighthouse crossing a foggy sea. And every time one of those beams crosses Earth, our telescopes catch a pulse, a flash, a whisper, a tick. The rhythm can be so precise that it rivals the stability of an atomic clock. Picture yourself beside one floating a few hundred kilometers above its surface. You can see nothing but the glare of its magnetic fields, ribbons of charged particles moving at nearly the speed of the light. The poles glow blue-white, flaring like open wounds in the fabric of space. The rotation is staggering hundreds of turns per second, each faster than a blink. If you could somehow stand there, you would spin around the star before finishing a breath. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell. She noticed a series of radio pulses repeating every 1.337 seconds, so regular that the research team briefly called it LGM-1 for Little Green Men. For a moment, humanity wondered if we were hearing an alien signal, but the truth was far stranger. It was the voice of a dead star, its magnetic field and rotation working together to turn decay into rhythm. You and I could compare it to a heartbeat after death, the final energy of collapse, transformed into motion so perfect it can measure time itself. If one of these pulsars replaced our sun, daylight would blink in rapid bursts, each separated by milliseconds. The solar system would become a strobe-lit cathedral of shadows, where light itself arrives in beats. Let's translate the numbers into something our senses understand. A pulsar rotating 700 times per second, or 707 Hertz, means that its equator moves at about 20% the speed of light, nearly 60,000 kilometers per second. That's fast enough to circle Earth 7 times in 1 second. Its magnetic field could lift the entire mass of Jupiter if it had something to grip, and yet this whole object, no larger than a city, spins in perfect silence, as if the universe were counting the seconds through it. You might wonder how it survives such violence. The answer lies in symmetry. The faster it spins, the more the outward force balances gravity. Like a dancer spinning on one foot, its motion keeps it upright against collapse. But balance, as we've learned, is temporary. The star is trading time for stability, shedding energy in every pulse, slowing imperceptibly like a heartbeat stretching towards stillness. From where we float, each flash feels almost tender. It reminds us that even in death, stars find ways to speak. The pulses still echo behind us, steady, hypnotic, like the ticking of a cosmic metronome. But every beat hides a mystery. How can something so small move so fast? How can a star heavier than the sun spin hundreds of times per second without tearing itself apart? We trace the origin of that impossible speed back to the moment of collapse, the death cry of a giant. When the star's core imploded, it carried with it a rule as ancient as the universe itself. Angular momentum must be conserved. It is the same principle that keeps a spinning top upright or makes an ice skater rotate faster when they pull their arms in. As the dying star shrank from millions of kilometers to only 20, the conservation of spin forced its rotation to accelerate thousands of times over. Imagine this if our sun, now turning once every 25 days, suddenly shrank to the size of Manhattan. While keeping all its spin, its new day would last less than a millisecond. That is what happens to the remnants of collapse. A stellar core once moving lazily becomes a machine of speed and silence. And yet even that initial acceleration is not enough to explain the extremes we observe. Some neutron stars rotate not hundreds, but over 700 times per second, a rate that would fling most matter into space. The fastest known PSR J0952-0607 spins 707 times per second. To maintain such speed, it must have been reawakened. You and I can picture it, a neutron star drifting in darkness, a silent relic cooling slowly until gravity finds it a partner. Another star, smaller and less massive, circles nearby. Over millions of years, gravity begins to pull material from the companion, stripping gas atom by atom, spinning it into a disk of fire around the neutron star. This process is called accretion, the slow theft of matter. Every droplet that falls adds momentum, turning the neutron star into a whirlpool of fury. The mathematics of it are beautiful. When a single gram of hydrogen spirals in it, releases more energy than burning a ton of coal. Now imagine billions of tons flowing every second. That energy becomes spin. The neutron star, once inert, becomes a millisecond pulsar, a resurrected heart. It now shines not by fusion but by motion, its speed powered by the hunger for mass. This process creates what astronomers call black widow pulsar systems, where the neutron star devours its companion. The name fits: the closer the partner drifts, the faster it is stripped. In some systems, the neutron star's beam of radiation becomes so intense that it literally evaporates the donor star, blasting it with X-rays until only vapor remains. You could call it cosmic cannibalism or a survival instinct written into gravity itself. Let's compare the scale. The surface of a millisecond pulsar moves at nearly 60,000 kilometers per second. If you stood on its equator, an impossible thought, you would circle Earth in less than 1/10 of a second. Its magnetic field can reach about 100 million Tesla, strong enough to erase data on every hard drive on Earth from as far away as the Moon. And all of this is contained in a sphere no wider than a city. If you listen carefully to the rhythm, each pulse tells the same story, motion feeding on loss. The faster the pulsar spins, the more mass it has consumed, but it is also burning its future. Every rotation emits radio waves, X-rays, and gravitational ripples. Slowly and perceptibly, it bleeds energy back into the cosmos. One day it will slow again, a whisper fading into the background hiss of the galaxy. You might say that speed is its way of refusing death for a while. We too live by momentum, by the balance between what we hold and what we lose. The pulsar only exaggerates this truth, turning it into light. The rhythm of the pulsar still flickers across the dark, fast and precise, but speed alone cannot explain its hunger. Something feeds it, something invisible orbiting close, being slowly torn apart. The universe has its predators, and this is one of them. Astronomers call it a black widow pulsar, a neutron star that devours its companion atom by atom until nothing is left. You can picture it easily: a pair of stars locked in orbit, one living, one undead. The living star, perhaps smaller than our sun, circles too close to the collapse remnant. Each orbit gravity steals a little more of its surface. Gas streams from the companion like ribbons of fire, forming a glowing disk around the neutron star, the accretion disk. The friction inside that disk releases enormous heat, thousands of times brighter than the sun's light, though most of it shines in X-rays invisible to our eyes. Now imagine what happens next. As that matter falls inward, it carries angular momentum, a spin boost. Every drop that lands on the neutron star adds speed, tightening the balance between gravity and motion. The more it eats, the faster it turns. Some of these cannibal pulsars reach over 700 rotations per second, faster than any other spinning body known. The act of feeding keeps them alive, but also pushes them closer to instability. Let's make that scale tangible. If the neutron star were the size of a city, its partner might be no larger than Jupiter. At a distance of only 1 or 2 times the width of our sun, it circles so quickly that one year there lasts just a few hours. From space, you would see a beam of light sweeping through the dark like a rotating blade, slicing through the atmosphere of the smaller star. Each flash strips atoms away, throwing them into orbit where they spiral inward until the neutron star consumes them. On Earth, such violence would seem impossible, but the physics is exact. The Black Widow pulsar PSR B1957+-20, discovered in 1988, was the first of its kind. Its beam of radio energy was found to dim periodically, not because it failed, but because clouds of gas from the dying companion star blocked its signal. Those clouds are the ashes of a partner being eaten alive. Over time, this cannibalism can completely vaporize the companion, leaving only the pulsar behind, solitary, still spinning, a widow in every sense. If you could hover nearby, you'd see something beautiful and terrifying. The small companion glows a deep orange, its surface boiling under the radiation. Each minute, its outer layers boil away into space. The side facing the pulsar is hundreds of degrees hotter than the dark side. The system looks almost like an eclipse, one star chasing the shadow of another. The light flickers pulse by pulse, not random but rhythmic like breathing. Let's ground that energy in something familiar. In 1 second, the pulsar's beam releases more power than all human civilization will ever produce. A teaspoon of matter falling into the neutron star releases as much energy as 100 hydrogen bombs. The magnetic field near its poles, about 100 million Tesla, could strip electrons from your body at a distance of hundreds of kilometers, and yet the entire structure remains balanced orbit after orbit, held together by gravity's perfect arithmetic. You might think of it as a cosmic addiction. The pulsar cannot stop feeding because feeding keeps it spinning. The companion cannot escape because escape means being torn apart by tidal forces stronger than any machine could withstand. Together they exist in a state of eternal consumption, a dance where one partner shrinks and the other grows heavier, faster, more dangerous. And here lies the paradox: every gram it devours brings it closer to the Tolman-Oppenheimer-Volkoff limit, the maximum mass a neutron star can bear, before collapsing into a black hole. The very act that keeps it alive may also doom it. When that final threshold is crossed, the pulses will stop. The light will vanish. The widow will fall silent, consumed by her own gravity. We drift away from this deadly pair, their light fading behind us. The rhythm slows like a heartbeat, weakening after a fever. Ahead, another signal waits, even faster, even heavier, and far more unstable. Its name is PSR J09520607, the most dangerous of them all. The rhythm fades. Behind us, the last pulse of the Black Widow star blinks like a distant heartbeat, steady but tired. Its light slips into the dark, and for a moment space feels empty again. Yet somewhere ahead, another signal rises. Faster, heavier, stranger. We turn our instruments toward it, and the universe answers with a whisper so fast it sounds almost like a vibration. Each tick, every fraction of a millisecond, marks a rotation. Not 100 or 200 times per second, but more than 700. You can't count that fast. You can't even imagine motion that quick. The signal belongs to PSR J09520607, the fastest spinning neutron star ever discovered, a record holder on the very edge of physics. This is not an ordinary pulsar. It is a contradiction written in gravity. Its radius is only about 12 miles 20 kilometers, yet it packs in 2.4 times the mass of our Sun. The surface moves at nearly 1/5 the speed of light, and every rotation sends 2 beams of radiation sweeping across the galaxy like blades of lightning. One flick of its spin could vaporize everything within 1,000 kilometers. But even more extraordinary is the fact that it hasn't collapsed. Not yet. We can think of it as a dancer twirling on the lip of disaster, spinning so fast that motion itself keeps her from falling. The faster PSR J09520607 rotates, the more centrifugal force resists gravity's inward pull. That balance, delicate and temporary, may be the only reason this star still exists. If it slowed even slightly, its own mass could crush it beyond recovery. Let's translate that to scale. If this neutron star replaced our sun daylight on Earth, would flicker 700 times a second like the rapid blink of a colossal cosmic eye. The solar system would pulse with invisible radiation, yet from 14,000 light-years away, it appears as nothing more than a rhythmic murmur in the radio spectrum, a soundless tick, marking time in the dark. Astronomers first identified it using the low-frequency array in Europe, a telescope network sensitive enough to catch whispers from across the Milky Way. What they found was unsettling, a pulsar heavier and faster than theory predicted. According to the Tolman-Oppenheimer-Volkoff limit, the upper boundary of stability, no neutron star should exceed about 2.5 solar masses without collapsing into a black hole. PSR J09520607 rests dangerously close to that threshold, spinning just fast enough to delay its own death. And so, we are left with a haunting question. Is it truly stable, or are we observing an illusion, the last stable moments before collapse? Picture it a star so dense that a teaspoon of its matter would weigh more than a mountain. A surface so curved by gravity that light bends around it twice before escaping. A core where neutrons are pressed shoulder to shoulder, trembling against a pressure no law of physics should allow. Inside, perhaps matter is already giving way, slowly, silently, one particle at a time. You can almost feel the tension from here. Each pulse that reaches us carries not just light, but warning, a record of motion buying time. Every rotation is a bargain with gravity. The star trades speed for existence, radiating its future away with each tick. We floating in its distant glow become witnesses to a clock that may be running out. Scientists call it the most massive pulsar ever confirmed. But perhaps it's something more, a cosmic edge case, the universe testing how close it can come to breaking its own rules. And we listening from afar can sense the inevitability beneath the rhythm, because even motion, even light, cannot outrun the hunger of gravity forever. The pulse of PSR J0952-607 still cuts through the dark 700 rotations each second like a heartbeat racing against fate. But beneath that rhythm lies something fragile, an invisible threshold where stability ends. The star spins not for beauty but for survival. It is balancing on the edge of a physical law, the Tolman-Oppenheimer-Volkoff limit, or simply the TOV limit, the final weight a neutron star can bear before gravity wins for good. You and I can think of the TOV limit as a kind of cosmic rulebook written by the mathematics of general relativity. It defines how heavy matter can become before no known pressure, not quantum, not nuclear, can stop collapse. The theory, first described in 1939, suggests that if a neutron star exceeds roughly 2.5 to 3 times the mass of the Sun, it will no longer exist as a neutron star at all. It will fall inward, crossing its own event horizon, and become a black hole. Imagine a rope stretched so tight that it hums in the vacuum of space. Every vibration threatens to snap it. That's what PSR J0952-0607 is, a rope of matter pulled to its limit, trembling under tension. The faster it spins, the more the centrifugal force resists gravity's inward pull. Yet that same spin drains energy over time, a slow leak that will one day remove the very balance keeping it alive. Let's picture it in numbers. If this star slowed by even a single rotation per second, a drop of less than 0.1%, the equilibrium might break. The crust, thinner than a fingernail compared to the core, would no longer withstand the pressure. Neutrons would collapse into pure gravitational confinement. The magnetic field would twist violently, tearing the surface apart in silence. In that instant, the pulsar's light would vanish, not in a flash, but in a quiet implosion, a fall into its own shadow. This limit is not hypothetical. Astronomers have already seen clues. Several neutron stars discovered near 2.3 or 2.4 solar masses behave as if teetering on the edge, their pulses unstable, their energy bleeding into gravitational waves. PSR J0952-0607 is the most extreme example, perhaps already flirting with that invisible line. It's a fascinating paradox. The very mass that gives the pulsar its power is the same mass that threatens to destroy it. Add just a few 100,000ths of a solar mass, the equivalent of 1 or 2 Earths, and the star could cross the point of no return. In cosmic terms, that's like placing one pebble too many on a mountain and watching the entire peak slide into the sea. Now, imagine standing nearby, if nearby can mean thousands of kilometers away, and feeling the tension in space itself. The star's gravity is so extreme that time slows near its surface. A second there might equal several seconds out here. From our point of view, the collapse would seem to happen in slow motion, frozen in its own descent. But from the star's frame, it would vanish instantly, slipping through the horizon where even light cannot escape. This is the difference between stability and surrender. A neutron star survives by pressure, the degeneracy of neutrons pushing outward, refusing to occupy the same quantum state. But once gravity compresses them beyond that point, even quantum law ceases to resist. Space-time curves too sharply, the fabric folds inward, and the star, this perfect spinning clock, collapses into mathematical invisibility. Let's bring the scale home. If the same TOV limit applied to Earth, our planet would have to shrink to less than 1 centimeter in diameter before collapsing into a black hole. The entire human race, every ocean, mountain and sky pressed into a sphere smaller than a marble. That's what the neutron star resists every second of its life. Yet there's beauty in this struggle. Each rotation of PSR J0952-0607 is not just survival, it's defiance. It spins as if daring the universe to stop it. And we, from 14,000 light years away, measure its courage with the precision of physics. Every pulse that reaches our detectors is a data point, a message, a confession. I am still here, it seems to say, but not for long. Some scientists believe the star may already have crossed the threshold, and what we observe is a ghost radiation from an object that has technically fallen, but whose last light is still reaching us across time. Others argue it remains barely stable, spinning just fast enough to hold its shape. Between those two ideas lies an extraordinary truth. The line between life and collapse in the universe is not sharp. It's blurred by time distance and relativity. And if that collapse comes, it will not shout. There will be no supernova, no burst of visible light. Only a quiet severing. The pulses will stop, the signal will die, and the universe will grow a little darker. The event horizon will swallow everything, even the memory of motion. We listen now, waiting for that silence. Because one day, maybe tomorrow, maybe in a million years, that perfect rhythm will end. And somewhere across the void, the star that held itself together for eons will finally fall, leaving behind nothing but gravity's hum, a ripple through space-time, a whisper that once there was light. The pulses of PSR J09520607 still reach a steady, defiant, hypnotic. Each flash of light marks survival. Each beat is a calculation in gravity's ledger. But deep within the star is paying for its speed. What keeps it alive is also what is slowly killing it. It is in the most literal sense eating itself to death. Let's return to how this began. PSR J09520607 was not born spinning at 700 rotations per second. It was remade. Once long ago, it was a quiet neutron star cooling, fading nearly still. Then gravity found it a companion, a small trembling star drawn too close. The neutron star began to feed pulling gas from its neighbor through a bridge of plasma. That gas formed a glowing whirlpool around it, an accretion disk billions of degrees hot, where atoms collided at a fraction of light speed before falling inward. Each drop that landed carried not just mass, but momentum. With every stolen breath of hydrogen, the neutron star spun faster. It fed with such efficiency that its companion began to shrink, stripped of its atmosphere, its core, and finally its shape. This is the story of the Black Widow system continued, but PSR J09520607 went further. It didn't just consume its companion, it transformed its victim into a fuel line. Imagine standing beside that whirlpool. The accretion disk glows brighter than a million suns, yet invisible to human eyes, burning in ultraviolet and X-rays. Gas falls toward the surface, striking with enough force to melt atomic nuclei. That energy converts to heat, and heat to radiation, a process so complete that it releases 20% of the mass it consumes as pure light. Nothing humans have ever built comes close, but that same process turns parasitic. The star spins so fast that centrifugal force flings part of that matter back into space, forming jets, twin columns of plasma shooting from its poles. In doing so, the neutron star wastes energy, throwing away what it just consumed. It's the universe's cruel symmetry. To survive, it must burn faster. The irony is beautiful and tragic. Each particle of mass that lands on PSR J09520607 pushes it closer to the TOV limit we explored before. Each new gram increases the gravitational strain, bringing it nearer to collapse. Like a candle that burns brighter, the closer it is to the end, the pulsar glows more fiercely the more unstable it becomes. Its hunger is infinite, but its stomach is finite. Now think of the numbers. At the current accretion rate, perhaps 1 billion tons per second, even a microscopic imbalance could push the mass beyond stability. Just a few trillion extra tons, a fraction of what it's already consumed, might be enough. That's less than what Earth gains in cosmic dust every 1,000 years. Yet for this star, it's the difference between motion and annihilation. If you and I could watch the final stage unfold, we would see light bending in strange patterns. The star's surface would blur, the magnetic poles twisting, as gravity began to overpower the rotation. The pulses would slow one by one, their rhythm faltering. Then at last there would be silence, a perfect clean stop. No explosion, no warning, just the end of light. Scientists call this a silent collapse. The neutron star doesn't announce its death. It simply exceeds the weight that physics allows. One moment it exists, the next it doesn't. Space-time folds over it, sealing it inside an event horizon smaller than a city. We can only imagine what happens in those final milliseconds. Does the surface disintegrate, or does it melt into gravity's geometry without resistance? Does the magnetic field snap, releasing one final wave of radiation? Or does it vanish quietly, its energy absorbed into the curvature of space? We don't know. But we can guess that the transition would create a brief pulse of gravitational waves, a whisper through the fabric of reality, the final heartbeat of a star that spun itself to death. And if that signal ever reaches us, it will tell a simple truth that even the most powerful engines in the universe cannot escape their own hunger. Every light we see is temporary. Every rhythm we hear will someday break. PSR J095/2-0607 is a reminder that power is never free, that survival at the cosmic scale is a kind of slow suicide. So we keep listening, one pulse then another, the star keeps eating, the light keeps shining. But inside the countdown continues a dance of balance and destruction, where each spin is both a victory and a wound. Eventually there will be a last rotation, and when it comes there will be no sound, only a faint ripple in space spreading outward, carrying the final memory of a star that lived too fast, burned too long, and devoured itself to survive. It ends quietly. The last pulse of PSR J095/0607 reaches us like a heartbeat too faint to count, and then nothing. No final flash, no fading light, no scream of energy, just stillness. The signal stops. From across 14,000 light years, it looks like the star simply turned off. But we know better. Somewhere out there, deep within its gravity, balance finally broke. The spin that had kept it alive slowed by a fraction too much. The weight it carried exceeded what physics could allow, and in that instant the universe reclaimed it. We are listening, you and I, through instruments tuned to radio waves and X-rays, through data streams that convert silence into meaning. The pulsar's rhythm, once perfect, mechanical, reliable, disappears from every channel. It's as if a clock that had been ticking since before humanity's dawn suddenly forgot the next second. This is the moment scientists call a silent collapse, a star falling inward without an explosion. There is no supernova, no shockwave, no light show. All that power, all that density simply folds into itself. It's gravity's cleanest work, ruthless, efficient, absolute. Imagine standing at a safe distance far enough to watch, but not to be destroyed. The surface of the neutron star begins to blur its outline, trembling under its own gravity. Light once racing away now curves back, trapped in circular orbits that never escape. For a fraction of a moment the star's glow doubles, not because it brightens, but because its light bends around itself, forming a perfect halo. Then without a sound, it is gone. To the universe, this event is almost nothing. No shockwave spreads, no gas erupts, only the disappearance of a rhythm. But to those who had listened to the astronomers and dreamers tracing its pulse through time, it is the loss of a voice. For years, the star had spoken in numbers 700 rotations per second, 2.4 solar masses, magnetic fields in the millions of Tesla. Each fact was a word in a long cosmic story. And now the story stops mid-sentence. If you could slow time, you would see something hauntingly beautiful. Space around the star stretches like molten glass, bending inward as the core collapses. The event horizon forms an invisible border where escape becomes impossible. Within that boundary, every law we know ceases to apply. Matter no longer has texture or structure. It becomes pure geometry, pure gravity. A star that once defied physics now is physics a whole where rules bend. Back on Earth, our telescopes register only absence. The steady pulse line becomes flat. Observatories mark the time, PSR J0952-0607, no longer detectable. For some it's a technical note, for others it feels like a funeral. A light that had crossed 14 millennia to reach us has finally gone dark, not because it ran out of fuel, but because it crossed the last frontier of existence. And yet, silence in the universe is rarely empty. Even when the light dies, something else moves. The collapse that created this quiet released ripples in the fabric of space-time gravitational waves, faint vibrations that travel not through air, but through reality itself. They pass through galaxies, through stars, through us, changing distance and time by less than the width of an atom. But they are there, the last breath of a fallen star. We cannot see them, but we can listen. Detectors like LIGO and Virgo stretch their mirrors to impossible precision, waiting for a tremor, a whisper, a sign that somewhere in the dark another collapse has occurred. And when they hear it, it's not a roar, it's a hum, a deep passing tone that says something heavy just vanished. So the silence of PSR J0952-0607 is not the end. It is the beginning of another story, one told not in light but in gravity itself. The silence does not last. From the heart of that vanished star, something awakens not in light but in motion. Though PSR J0952-0607 has fallen past the edge of visibility, the space around it begins to scream in energy. The material that once orbited it, The debris, the fragments of its companion, the residue of accretion is now trapped in a final, desperate spin, and when gravity and magnetism align, the result is violent beauty relativistic jets. Imagine two narrow streams piercing through darkness like spears of lightning. They are made not of light but of matter, electrons, positrons, ions, hurled outward at almost the speed of light. Near the poles of the newborn black hole, magnetic lines twist and tighten, converting rotation into thrust. The energy released is staggering, more than 100,000 times the brightness of our sun compressed into twin beams no wider than a city. To see such an event from afar would be to witness creation in reverse. The same forces that once built stars now tear them apart. Around the new black hole, an accretion disk still glows, an orbiting furnace of plasma, heated to billions of degrees. As its inner edge spirals toward the event horizon, friction and magnetic shear create a sudden imbalance. That imbalance focuses energy into the jets ejecting particles across thousands of light years. It is nature's own particle accelerator, dwarfing anything humans could ever build. Let's translate the scale. If one of these jets pointed toward Earth even from 14,000 light years away, the radiation would sterilize our planet. The ozone layer would evaporate, the atmosphere would fluoresce, and the night sky would ignite with a strange blue glow. Luckily, we are not in its path, but we have seen the signatures of such events elsewhere, ancient records written in the scars of extinction. Roughly 440 million years ago, at the end of the Ordovician period, the fossil record shows a sudden catastrophic loss of life. Over 80% of marine species vanished. For decades, geologists sought to cause volcanoes' climate shifts, asteroid impacts. But one hypothesis remains chillingly elegant, that a gamma ray burst from a nearby collapsing star stripped Earth's atmosphere of its shield, letting lethal ultraviolet light from the sun burn through the oceans. Perhaps not this pulsar, but one like it. The universe does not need to be close to be dangerous. The energy in a relativistic jet is so concentrated that a single burst lasting just 10 seconds can release more power than our sun will emit in its entire 10 billion year lifetime. And yet such bursts happen regularly, hidden in galaxies beyond the reach of ordinary eyes, each one rewriting the landscape of space in its own silent way. If we could stand near such a jet, it would not look like fire. It would be colorless, invisible to human sight, pure radiation. The surrounding space would shimmer as atoms ionize and reform. The magnetic field, trillions of times stronger than Earth's, would stretch light itself into spirals. Even at a distance of thousands of kilometers, our atoms would shake apart. To observe it safely, we must rely on instruments, radio arrays, gamma detectors, space telescopes that turn the invisible into sound and data. What they reveal is astonishing. Jets do not move in straight lines. They twist and precess, guided by the black hole's spin. As the disk feeds, the black hole itself wobbles, changing the jet's direction over time. These cosmic lighthouses sweep their deadly beams through galaxies like scythes, reshaping everything in their path. Some even spark new stars in distant regions, compressing gas clouds into collapse. Destruction and creation perfectly balanced. You might think of it as a heartbeat continuing after death. Though the star is gone, its energy remains reorganized, redirected, reborn. The collapse that seemed final becomes a trigger for new beginnings. The jets carry matter and information into interstellar space, seeding it with heavy elements, gold, platinum, uranium materials forged in violence. In a strange way, we owe our existence to explosions like these. Every atom of gold in your body once belonged to a dying star. And so, when we imagine the death of PSR J0952-0607, we must also imagine its afterlife. Its pulse is gone, its light extinguished, yet it still speaks in particles racing outward in gravity, bending the paths of time in radiation that may one day touch another world. Even now, the faintest fraction of that energy may still be moving toward us, a whisper we will not hear for thousands of years. We drift in silence again, the jets fading to ghostly streaks on our detectors. Somewhere behind us, space closes its wound, the black hole stabilizing the violence, settling into order. And just beyond this calm, another kind of storm is waiting, not one born of collapse, but of magnetic fury, where gravity's silence turns to the roar of fields, strong enough to tear matter apart. The light is gone and the jets have faded into distance. For a moment it feels as if the universe has gone still again, a silence so complete it almost feels sacred. But silence in the cosmos is never empty. beneath the quiet space itself begins to move. It stretches, it compresses, it vibrates. This is the second signal, not light, not radiation, but the trembling of the universe itself. We call it a gravitational wave, a ripple in the very fabric of space-time created when something unimaginably massive changes shape. When PSR J09520607 finally collapsed, the symmetry of its spin shattered. Matter spiraled inward, dragging gravity with it, distorting the geometry of reality. That distortion became a wave spreading outward across the galaxy at the speed of light. You and I can't feel it, but we are moving through it right now. Every second, hundreds of these waves wash through Earth, faint elusive, changing the distance between atoms by less than a fraction of a proton's width. Yet, we have learned to listen. On quiet nights, observatories like LIGO in the United States, Virgo in Italy, and Kakura in Japan stretch their laser arms across kilometers of space, waiting for that microscopic shiver. When it comes, it doesn't make a sound, but it carries a story. Imagine what this wave remembers. It remembers the moment gravity conquered light. It remembers the twist of space when the star folded into itself. It remembers the final heartbeat of PSR J09520607. The instant rotation stopped, and everything that had been became geometry. As the wave passes through, it leaves behind a faint change in time itself, a rhythm too deep for the ear, too wide for the eye. When the first gravitational wave was detected in 2015, it came from two black holes, colliding over 1 billion light-years away. The event lasted less than half a second, yet it proved Einstein's prediction, after a century of waiting. It told us that gravity was not just a force, but a messenger. It can carry emotion, memory, violence across the universe, across ages. Now we wait for the echo of our fallen pulsar. If its collapse was asymmetric, if even a fraction of its matter resisted the fall, the resulting wave would be brief, sharp, and haunting. A spike in the data, a cosmic exhalation. And if we catch it, we will have recorded something no telescope can ever see: the death of a star from the inside out. Picture space-time as a vast invisible ocean. When a massive body moves, it sends ripples through that sea. A neutron star's collapse is a stone dropped from infinity, the rings spread endlessly outward. For billions of years, they travel unchanged, carrying the signature of what happened in those final milliseconds. Somewhere among those ripples, the coordinates of PSR J09520607 are encoded, a timestamp of gravity's victory. What fascinates scientists most is how silent these waves are. They carry no light, no heat, no particles, only motion itself. They are the most honest witnesses in the cosmos. While light can be blocked, scattered, or absorbed, gravity waves pass through everything untouched. They are in a sense the heartbeat of creation, the pulse beneath all pulses. You might wonder what it feels like to hear one. To scientists, it arrives as a curve, a faint chirp in data, rising, falling, then gone. But if you translate that curve into sound, it's like a low, drawn-out sigh. That sigh is the memory of a star, recorded not in light but in curvature. And it tells us something profound: nothing in the universe truly disappears. When light fades and matter collapses, gravity remembers. It writes history not in flame but in motion, so we keep listening. Every ripple, every tremor that passes through us could be the echo of another death, another birth, another law rewritten. Somewhere far beyond our reach, the universe is still whispering, not in words but in waves. As we drift away from the remnants of PSR J09520607, the hum of its collapse fades beneath us, but the idea lingers that even in silence the cosmos speaks. And sometimes the faintest vibration carries the loudest truth. The hum fades. Behind us, the echoes of PSR J09520607 dissolve into the deep fabric of space, its light extinguished, its gravity still trembling in silence. Yet even as the universe quiets, a new kind of storm begins to rise. This time not born of collapse, but of tension. Gravity bends space, but magnetism, it shreds it. You and I drift now toward a different kind of star. It spins slower, but the air around it, if air could exist here, would rip apart every atom you know. Its surface glows with the cold fury of compressed energy, and above it arcs an invisible architecture of unimaginable strength. This is a magnetar, a neutron star whose magnetic field is the strongest ever known. If PSR J09520607 was a dancer spinning at the edge of gravity, the magnetar is a sculptor reshaping space itself. Its field can reach 10 to the 15th Gauss, that's a trillion times stronger than Earth's magnetism. To put it in perspective, the field of a magnetar could erase every hard drive on Earth, even from the distance of the Moon. And if you were to stand just 1,000 kilometers away, the magnetic pressure would tear apart the molecules in your body, ripping electrons from atoms, forcing matter itself to dissolve. Let's imagine it gently. You're hovering in a silent void, watching a star no larger than a city. Its surface boils not with fire, but with invisible lines of force. Iron atoms on its crust stretch into threads. The vacuum around it shimmers, bending photons, creating halos where light shouldn't exist. You raise your hand, and if you could feel the field, it would be like touching the breath of a god unseen, cold, infinite. Magnetars are rare, perhaps 1 in 10 neutron stars, yet they embody the most extreme form of electromagnetic order nature allows. The origin of this power lies in the chaos of their birth. When a massive star collapses, its magnetic field lines are squeezed inward. Like winding a spring too tight, this compression amplifies the field to monstrous strength. Then rotation locks it in freezing magnetism into matter. But nothing in the cosmos remains stable forever. The same magnetic field that gives the magnetar its identity also strains it toward destruction. The crust of the star, though incredibly dense, is under constant stress from below. Imagine the ground beneath you vibrating with forces billions of times stronger than the pull of Earth's gravity and yet silent. The magnetic tension grows, knotting itself like cords of steel beneath the surface, waiting for one twist too many. This is where the danger begins. When the crust finally yields, the stored energy doesn't fade, it erupts. For a brief moment, the star's magnetic field realigns, snapping like a whip across space. The result is a flare of X-rays and gamma radiation so bright it can outshine every star in the galaxy for a heartbeat. The strongest of these outbursts ever recorded came from SGR 1806-20, a magnetar 30,000 light-years away. In December 2004, its magnetic crust cracked, and for 1/10 of a second, Earth's ionosphere shook, as if struck by a hammer. Satellites flickered, radio signals vanished, and our atmosphere absorbed a burst of energy equal to that of the Sun in 250,000 years, and that was from halfway across the galaxy. We survived because distance is mercy, but the numbers remind us how fragile we are, how close our instruments sit to forces we cannot comprehend. If you could see magnetic lines as colour, a magnetar would not be a star but a cathedral of light, a structure of living geometry. You would watch fields curve around it like ribs of luminous glass, each one glowing faintly as particles stream along invisible paths. The entire cosmos would seem to breathe with it, pulsing in silent rhythm. We leave behind the dead pulsar and now face something different, not death but tension. Not collapse inward but power stretched to breaking. And soon, when that strain gives way, the magnetar will quake. The magnetar holds its breath. From a distance it looks peaceful, a dim ember suspended in the dark. Yet beneath its calm surface unimaginable pressure builds. Magnetic lines twist and strain, pressing against the crust of the star like invisible hands. You can almost hear it, the deep vibration of stress that never stops. The entire star is a wound wrapped in light. You and I drift closer. There is no sound here, no air to carry it, but the silence feels alive. Beneath the surface of this city-sized world, forces battle gravity trying to compress magnetism, trying to escape. For years, decades, even the tension grows, building inside a shell only a few kilometers thick. It is harder than diamond, yet softer than the field it contains, and one day it gives way. When a starquake begins, it doesn't start like an earthquake. There is no warning, no tremor. Instead, the magnetic field suddenly rearranges itself. The crust cracks, releasing a flood of trapped energy. Imagine a mountain-sized fault line breaking all at once, not in rock, but in nuclear matter. For a fraction of a second, more energy is released than our sun emits in 100,000 years. The space around the magnetar becomes a storm of light. Gamma rays and X-rays burst outward, tearing across the vacuum like invisible fire. The blast front races past our instruments, reaching across light years in seconds. For a brief moment, the magnetar shines brighter than all the stars in its galaxy combined and then fades back into silence. We've seen this happen. In 1979, detectors aboard the Soviet Venera spacecraft recorded a mysterious flash that blinded sensors across the solar system. It came from a magnetar now known as SGR 052666, located in the Large Magellanic Cloud 165 0.00 light-years away. The burst lasted only 0.2 of a second, yet it saturated every gamma-ray detector on Earth. Later in 2004, SGR 1806-20 erupted, releasing more energy than the Sun could in 250,000 years, and we felt it here across half the Milky Way. If a magnetar that distant can shake our planet's ionosphere, imagine what one just 40 light-years away could do. The gamma flare would strip away the ozone layer in moments. Ultraviolet light from the Sun would pour down, sterilizing the oceans, bleaching the sky white. The very air would fluoresce glowing blue, not from beauty but from destruction. And yet the magnetar itself would remain untouched. The explosion does not destroy it, it only resets it. The field realigns, the crust heals, the tension starts to grow again. In 1,000 years, maybe 10,000, it will happen. Once more, a cosmic heartbeat made of catastrophe. Think of how strange this is. A starquake lasts less than a blink, yet it rewrites the chemistry of entire regions of space. It floods the interstellar medium with particles and heavy elements. It can trigger the birth of new stars in clouds of gas 100 light-years away. Death and creation forever intertwined. Let's translate that scale to something human. If the energy from one starquake could be captured, it would power every city on Earth for 1 billion years. If you could hold a single cubic centimeter of a magnetar's crust in your hand, impossible. But imagine it would weigh more than every skyscraper on the planet combined. That's how dense, how fierce, how tightly wound the physics of this world is. But there's more. Scientists suspect that during these starquakes, gravitational waves ripple outward, faint distortions in the structure of space itself. Not strong enough to destroy, but detectable, like the heartbeat of a giant echoing through the void. Instruments such as LIGO and Virgo continue to listen for those ripples, hoping to match them with gamma-ray flares. If they succeed, it would mean we've heard a magnetar quake across the galaxy, a seismic whisper travelling through time. There is something poetic about that. Every planet quakes in silence, but this is a quake that shakes the fabric of the universe. A reminder that even in perfect vacuum, nothing is ever truly still. Imagine standing above it now. The surface glows with shifting light, molten cracks, bleeding energy. The magnetic field twists into loops that extend for thousands of kilometers, each one crackling with charged particles. And then, stillness again. The star returns to calm its surface, hardening the tension, rebuilding quietly beneath. We drift backward, letting the light fade. What we've witnessed is both terrifying and mesmerizing, the heartbeat of a dying universe, a pulse of power wrapped in silence. These magnetars live on the edge of control, their existence a cycle of violence and healing. They remind us that even in the vast coldness of space, stress and release still rule everything. But magnetism is not done with us yet, because somewhere out beyond the safety of distance, some of these stars are not content to stay still. They move, and when they move fast enough, they turn from monsters into projectiles, wandering threats that could one day drift toward our own solar system. The quake fades. The magnetar steadies itself once more, its crust sealed, its fury buried for now beneath layers of dense, unyielding matter. From afar it looks calm again, but calm can be deceptive. A storm like that never ends, it only waits. You and I drift at a distance of safety, or what we think is safety. Yet in a universe measured in light years, safe is a fragile word, because even when an object lies thousands of trillions of kilometers away, its presence still shapes the space around us. Magnetars remind us of that they are quiet now, but not harmless. Let's imagine one drawing nearer. Perhaps it was born in a distant supernova and thrown outward at incredible speed, 1,500 kilometers per second, faster than any bullet humanity has ever fired. It drifts through the galaxy like a silent projectile, its magnetic field cutting through interstellar space. At that speed, it could cross the distance between stars in less than 1 million years. The odds of it coming close to us are small, but not zero. So what if one day the impossible happens? If a magnetar entered our stellar neighborhood even tens of light years away, we would notice first through our satellites. Radio static, magnetic interference, compasses twisting wildly. The magnetosphere of Earth would tremble, distorted by invisible pressure. Power grids would hum with current that no one sent. The auroras at the poles would bloom into ghostly spirals brighter than daylight curtains of color woven by cosmic tension. Closer still, say within a few astronomical units, and the laws of normal matter begin to fail. Every wire, every electronic device, every hard drive would erase itself in an instant. The atoms in human bodies would subtly shift their electrons, forced into new orbits by the external field. Molecular bonds would strain. Iron in blood would respond faintly tugged by a force far older than life itself. At a few thousand kilometers, the real destruction begins. The magnetar's field, trillions of times stronger than Earth's, would start to rip electrons away from atoms entirely. Molecules could no longer hold their form. The air would glow faintly blue, ionized by radiation. The crust of our planet would feel gentle tides not from the moon but from the magnetic drag of an alien star. If it approached to the orbit of Jupiter, roughly 500 million miles, gravitational effects would add to the chaos. Planetary orbits would wobble, satellites would fall, and radiation would bathe the solar system. Even without touching us, the magnetar would turn our skies white. And if it came closer still, the magnetic pull would distort Earth's core. Oceans would rise in waves taller than mountains. The planet's own field would collapse, leaving us naked before cosmic rays. The atmosphere would shimmer, burn, and then fade. Communication would die. Electronics would be erased. The night would be filled with silent lightning electricity crawling along the surface of the planet, searching for a path to ground. But the magnetar wouldn't care. It doesn't destroy by will, but by nature. It carries its chaos like a star carries light. Now step back with me far, far away again. At 14,000 light years, as with PSR, meaning 520607, we are safe. We can study without fear. But this distance, this margin, is what saves us. A few dozen light years closer, and the difference between safety and extinction would vanish. That is the paradox of the universe. The very forces that forge life are the same ones that can erase it, and what protects us most isn't strength, but distance. Astronomers sometimes call this the danger zone, a sphere around any magnetar within which complex chemistry cannot survive. It is not a place of fire or explosion, but of unraveling, the quiet undoing of order. If a magnetar were ever to cross that boundary into our solar space, life would end not in flame, but in silence. So we remain here, tiny and fortunate, in a fragile orbit that has never yet been disturbed. The universe is filled with hidden fields and unseen storms, and our survival depends not on walls or weapons, but on space, empty, vast, merciful space. As we drift onward, leaving the magnetar behind, the thought lingers. The universe doesn't need to touch us to destroy us. Sometimes all it takes is for distance to disappear. The light of the magnetar fades behind us, its storm shrinking to a distant pulse. We drift once more into the quiet sea between stars, but that calm is deceptive. Out here, nothing truly rests. Every object, every grain of dust, every sun, every black hole is moving, and some are moving too fast for comfort. We leave behind fields of magnetic ruin and enter a new kind of danger motion itself. Because the universe is not static. It is a network of trajectories, collisions, and slingshots. Every explosion, every supernova, every gravitational tug creates motion. When a star dies, it does not simply fade, it launches fragments and remnants like cosmic shrapnel. And among those fragments are neutron stars. Some wander aimlessly, others are hurled away like bullets. This is how the most dangerous travelers in the galaxy are made, the runaway neutron stars. You and I can picture one being born. A massive star collapses, detonating in a supernova so fierce that it outshines 1 billion suns. The explosion is not symmetrical. One side pushes harder than the other, and the recoil launches the dense core into space. What remains of the star, no larger than a city, flies away at 500 kilometers per second, faster than the escape velocity of the Milky Way's own gravity. A bullet the mass of the sun, tearing silently through interstellar dust. It's hard to imagine that speed. If the Earth could move that fast, it would circle the sun in less than 3 seconds. If you fired a bullet at that velocity, it would reach the moon in under 5 minutes. The neutron star, however, carries not just speed, it carries momentum. Its mass gives it inertia so immense that no collision, no gravitational tug from ordinary stars can slow it. It is a traveller destined to drift forever. We have found traces of them. Astronomers call them runaway pulsars, and some leave behind visible trails, faint wakes of ionized gas glowing in X-rays. The pulsar B1528+55, discovered with the Very Large Array, is one such traveller. It's racing away from the galactic plane at over 1,000 kilometers per second, trailing a ribbon of light like a comet's tail made of pure energy. These objects are older than our species, older than our sun. They have been moving for millions of years, silent and invisible, until a telescope happens to cross their path. When we detect their signals, we're not hearing them as they are now, but as they were thousands of millennia ago, cosmic echoes of motion. Now imagine if one of these runaway stars were on a path toward us. Even from tens of light years away, its gravitational influence could ripple across our solar system. The delicate clockwork of orbits Jupiter, Saturn, Earth would begin to shift. A tiny drift at first, fractions of a second per century, but over time the resonance would grow. Planetary paths would stretch, twist and fall out of rhythm. At greater speeds, the neutron star would not even need to come close to be felt. Its gravitational bow wave would push interstellar gas ahead of it, heating the medium and stirring magnetic fields for light years. A rogue star crossing the outer edge of our system could strip comets from the Oort cloud, sending icy missiles inward, rewriting the sky one impact at a time. You might ask, would we see it coming? Perhaps. A faint infrared glow, a shifting pulse in a sky map. But it would move faster than anything we've ever tracked, crossing the distance between stars while we argue about its name. There's something haunting in that thought, a star the size of a city moving faster than any human-made machine carrying the weight of the sun, indifferent to anything in its way. A relic of destruction travelling through time and distance without purpose, yet capable of rewriting entire worlds. And soon as we follow one of these travellers deeper into the dark, we'll see what happens when such a runaway intruder comes too close, when the solar system itself trembles under the weight of a passing star. We follow the traveller. It drifts through the dark at impossible speed, a neutron star, the remnant of some ancient cataclysm, racing silently through the interstellar void. It is small enough to fit inside a city, yet it carries the weight of 2 suns. Every second it moves another 1,500 kilometers closer to nothing in particular. There is no destination, no intent, no mercy, only motion. Now imagine this is where the mathematics becomes haunting. Imagine that its path cuts across our own. Perhaps not directly, but close enough for gravity to notice. A few light years then, a single one. The distance shortens. The outer edges of our solar system, the realm of icy comets and drifting debris, feel the first pull. They begin to stir. At first the changes would be invisible. Tiny perturbations in the orbits of distant objects. The outer planets would drift by fractions of degrees. But with each year, the dance of resonance between worlds would grow unstable. Jupiter, our giant guardian, would shift slightly in its orbit, perhaps only by 1 million kilometers. Yet that small movement would echo inward. Saturn's rings would distort. Uranus and Neptune would wander in rhythmless ellipses. And far beyond the Oort cloud, a vast halo of frozen relics would fracture. Comets, thousands of them, would break free and fall inward toward the sun. Their long icy tails would flare through the inner solar system, each one a warning line across the sky. Earth would not be struck immediately, but night after night the heavens would fill with strange motion, new stars streaking, moving too quickly, growing brighter as they burned. Let's consider what happens if the neutron star comes closer still. At a distance of 500 million miles about the orbit of Jupiter, gravity would begin to reshape everything we know. Jupiter itself, massive as it is, would feel the tug. Its path would elongate, then tilt. Saturn's perfect spacing, the delicate geometry of its moons and rings, would begin to warp. Orbital chaos would spread like a wave. The sun's balance would not survive untouched. Its gravitational focus would shift by tiny amounts, imperceptible at first. But those tiny shifts would disturb the whole planetary clockwork. Mercury's orbit would wobble. Venus would drift closer. Earth's year might shorten by seconds, then hours. The moon, tethered by Earth's pull, would feel competing tides, one from home, one from the alien intruder. From Earth's surface, the sky would look wrong. Constellations would shift ever so slightly. Satellites would fall out of sync. The International Space Station would drift. We would watch helpless as gravitational laws, the same ones that had guided our calendars, our seasons, our tides, began to rewrite themselves. And then there is the light. Because neutron stars are not just heavy, they are radiant in deadly ways. As it approaches the field around it, glows with X-rays and gamma rays. The bow shock of its motion through interstellar gas produces a thin wake of plasma, glowing faintly in ultraviolet. Even at 1 billion kilometers, those rays would wash across our solar system, bleaching color from the planets, scattering radio waves into noise. If the neutron star is an active pulsar, its beams of radiation would sweep through space, like lighthouse beams crossing us periodically. Each pulse would be a flash of pure energy, invisible but devastating. The first to feel it would be our satellites. Circuits would die instantly. Communication would vanish. GPS constellations would blink out one by one. Then the upper atmosphere would begin to ionize and the ozone layer would crumble under the assault of high-energy photons. Imagine standing outside when it happens. The sky turns white-blue, but there is no warmth. The air crackles faintly with static. At night, the auroras expand not at the poles, but across the entire sky. Curtains of green and violet shimmer over deserts and oceans alike. For a few hours, the world glows breathtaking and deadly. The sun's light, usually gentle and familiar, now carries new danger. Without ozone, ultraviolet rays reach the surface unfiltered. Within weeks, crops wither. Skin burns in seconds. The oceans begin to fluoresce with disturbed plankton dying in bright streaks. The atmosphere hums with electricity storms forming without heat, thunder, without rain. This is not the fiery apocalypse of science fiction, it is slow, methodical disassembly. The gravitational tide of the passing star pulls gently but continuously. Over centuries, the orbits of planets drift farther from stability. Some spiral inward, others outward. The solar system becomes a broken mechanism still turning but off balance. The seasons lose rhythm. The axis of Earth begins to precess violently. Ice ages and infernos alternate with no pattern, no warning. And then one day something subtle changes. The neutron star passes the point of closest approach. It drifts on indifferent, leaving behind chaos it will never see. Gravity relaxes. Orbits begin to settle again, but nothing returns to what it was. Jupiter may have a new year. Earth's distance from the sun may change forever. The sky's geometry, the ancient constellations written in myth and memory, is now rewritten. Our instruments would record it as a set of numbers, as deviations in orbital mechanics. But from a human vantage point, it would feel like the cosmos had shifted beneath our feet, the invisible order we trusted replaced by a slower, stranger rhythm. And even after it is gone, the neutron star's touch remains. The comets it disturbed continue their inward fall, one by one, streaking the night with brief, beautiful fire. We would rebuild, perhaps, but we would remember the silence that moved through space, a reminder that in the vast balance of the universe, it takes only one passing star to unmake a solar system. The runaway star does not stop. It drifts on a trajectory drawn in ancient fire, silent, relentless, beautiful. We've seen what its gravity can do, the slow distortion of orbits, the quiet disassembly of order. But there is a deeper terror, one that does not rely on distance or mass. Because this traveller, like some of its kin, carries not only weight but magnetism, a field so fierce it can unmake matter itself. You and I stand now at the threshold of that field. There is no visible boundary, no glowing wall, no warning. Yet as we cross it, the laws of chemistry begin to weaken. The magnetic field stretches across millions of kilometers, but its reach is subtle. It begins by bending the paths of electrons, by persuading atoms to dance in patterns they were never meant to know. If this star is a magnetar, its field could exceed 10 to the 15th Gauss, 1,000,000,000,000 times stronger than the one guiding your compass on Earth. At that strength, hydrogen atoms, the simplest, most obedient building blocks of the universe, become distorted, drawn into long, thin filaments. The fabric of matter itself begins to deform. Imagine holding a spoon made of steel. At home it sits calm, solid, silent. Here within this invisible storm, the spoon would tremble. The bonds that hold its atoms together, magnetic and quantum, ancient and elegant, would stretch and stretch until they snap. Metal becomes dust, dust becomes plasma, and plasma under a magnetar's command becomes art sculpted into luminous arcs that trace the invisible geometry of its field. Let's go closer still. At just a few thousand kilometers, the field is strong enough to strip electrons from your body. Molecules dissolve, and what was once flesh becomes a drifting cloud of ionized gas. The mind, the bones, the heartbeat all unravel into charge. You wouldn't feel pain. There would be no time. The transition from life to plasma would happen faster than a thought. Now look at the planet below. If Earth were caught at such a distance, its atmosphere would ignite in waves of radiation. Every wire would hum with phantom current, every magnet would convulse. The global power grid would collapse in an instant. Satellites would fall from the sky, and auroras, vast blood-red curtains, would shimmer at the equator. Oceans would boil at their surface from induced electric currents. The moon's orbit would twist as Earth's core strained against competing magnetic tides. It would not look like an explosion. It would look like a quiet storm of light luminous tendrils stretching across the horizon, the sky trembling with motion. No wind, no thunder, just space itself humming. Scientists call this phenomenon magnetic reconnection, when opposing magnetic fields snap and rejoin, releasing stored energy. In the sun, it creates solar flares. In a magnetar, it creates apocalypse. When the field lines twist too tightly and break, they emit a torrent of gamma rays enough to sterilize planets from dozens of light years away. And yet what's most haunting is that it's all perfectly natural. There is no intention behind it, no anger, no malice. It's just physics pushed to its limit. Every atom, every field, every line of force obeying the same equations that govern your heartbeat, the same symmetry that binds galaxies. Only here those laws reveal their truest form power without mercy. Let's scale it to something familiar. If you could bottle a magnetar's energy for 1 second, it would power our civilization for 100 billion years. If you could fit it inside a city, the field would reach far beyond the moon. If one passed within a few astronomical units, the distance between Earth and the Sun, every electron in our technology would feel it. Every circuit, every signal, every thought conveyed by electricity would fail. The age of machines would end in silence. Yet amid that terror there is beauty. Because in a strange way, the magnetar is also a sculptor. It shapes the vacuum drawing lines of force like brushstrokes through nothingness. The light that escapes its surface is polarized, shimmering as if filtered through invisible crystal. Even destruction in the hands of physics becomes art. You can almost feel it now, that deep resonant hum under your feet, the slow, steady breathing of the universe. The magnetar's field swells, and for a moment everything feels connected: matter, light, gravity, time. It's as if the cosmos is reminding us you are made of the same rules that unmake you. Then the sound fades. The storm passes. The neutron star continues its drift indifferent once again. Behind it only silence and the memory of fields too strong for life to endure. We float once more into the darkness, leaving the shattered orbits behind. Ahead lies something quieter, not chaos but consequence. For even in ruin the universe remembers. And in the wake of destruction, sometimes life begins again. The storm of magnetism fades. The silence that follows feels heavier than before, the kind of quiet that only comes after something powerful has passed. Behind us lies ruin, bent orbits, shattered fields, a world undone by invisible hands. But even here, in the wake of annihilation, something extraordinary happens. When a star dies, it doesn't simply vanish. It leaves behind the tools for creation. Every explosion scatters elements: carbon, oxygen, iron, the raw alphabet of life. And sometimes, amid this chaos, matter begins to gather again. Dust circles debris. Gravity remembers what it once was. The ashes start to orbit their own ghosts. You and I drift now toward one of those impossible places, a system that should not exist. A pulsar planetary system. At its heart spins not a living sun, but a corpse, a neutron star, the remnant of a supernova. It rotates hundreds of times each second, sweeping its deadly light through space, like a cosmic beacon. Yet around this broken thing, planets orbit solid, quiet, persistent. This isn't imagination, it's real. In 1992, astronomers using the Arecibo Observatory detected faint rhythmic anomalies in the timing of pulsar PSR B27 12 Sud, 300 light-years away in the constellation Virgo. Those tiny delays, milliseconds of difference, revealed something unbelievable: planets tugging at the neutron star's gravity. The first confirmed worlds ever discovered outside our solar system weren't around a gentle sun. They circled a corpse. How could that be? A pulsar's birth is violence. When its progenitor exploded, every original planet should have been vaporized. No known world could survive a blast brighter than 1 billion suns. So how do these new ones exist? The answer, scientists believe, lies in the debris itself. After the explosion, some of the material falls back toward the neutron star, forming a disk of dust and heavy elements. Within that disk, gravity takes root again. Tiny grains stick together, build mass, and slowly over millions of years form planets from the ruins of death. They are worlds born from wreckage. Their skies would be forever dark, their light pulsing in violent rhythm. A day there would last milliseconds, the time it takes the pulsar to spin once. Imagine standing on such a planet: no sunrise, no sunset. Only the regular heartbeat of radiation sweeping across the landscape. The air, if any existed, would glow faintly under the bombardment of high-energy particles. The ground might hum with the steady rhythm of the parent star's spin. We can picture the geometry of survival here. Each planet must find a precise orbit far enough to avoid being vaporized close enough to stay bound. A few kilometers closer and it would disintegrate into dust. A few farther and it would drift away into the cold. Only the narrowest corridor of balance allows it to exist. And yet, they do exist. 3 confirmed planets nicknamed Draga Poltergeist and Phobator Circle, PSR B1702. Each name tells a story of haunting of persistence beyond death. Their surfaces may be frozen stone or molten metal, but their mere presence rewrites our assumptions about what can follow destruction. It's strange to think that in the dark under radiation that would annihilate as order can still emerge. Perhaps this is the quiet secret of the cosmos, that creation and ruin are not opposites but companions. Every explosion feeds another beginning. Every death leaves behind a pattern waiting to be rebuilt. As we drift around this ghostly system, the pulse of its star echoes like a metronome, steady, unrelenting, timeless. Each flash is a reminder that even in the aftermath of cosmic violence, gravity still remembers how to gather and light still insists on returning. The pulse continues. Behind every flicker of light from the pulsar there is rhythm, perfect, relentless rhythm. On worlds like Drauga or Poltergeist, that rhythm defines existence. There is no true day, no dawn, no dusk, only the repetition of death disguised as light. The pulsar's beams sweep through space like blades cutting through the void, washing each planet with waves of X-rays and charged particles. You and I hover above one such world now. Its sky is black, not empty, but thick with radiation and dust. The parent star does not shine like the sun. It flashes. Each pulse lasts less than a blink, but it floods the surface with energy strong enough to sterilize rock. Between pulses, darkness returns, an eternal restless night interrupted by violence. If we stood on that surface, shielded somehow deep beneath layers of rock or ice, we would feel the pulse as vibration more than light. The ground would hum faintly, quivering to the beat of the neutron star's spin. Imagine living under a clock that never stops ticking, whose seconds are carved into the crust of your world. These planets orbit closer to their parent pulsar than Mercury does to our Sun, and yet they are colder than Pluto. Radiation strips away any chance for atmosphere, leaving behind bare stone and dust. The only way life, if we can still call it that, could exist here is to hide, to burrow, to adapt to the pulse instead of fleeing from it. Scientists once dismissed such worlds as sterile, but later research revealed something astonishing. If the pulsar's magnetic field channels radiation unevenly, there may be shadow zones of relative calm behind the planetary horizon. Within those narrow sanctuaries, heat from radioactive decay or residual energy from the crust could maintain pockets of warmth. There, beneath kilometers of ice or iron chemistry might begin to stir again. Picture it, deep under the crust, liquid pockets trapped between layers of frozen minerals. The radiation above powers complex reactions indirectly by splitting molecules, energizing them, forcing matter to recombine in improbable ways. In those hidden oceans, perhaps the building blocks of life, amino acids, polymers, carbon chains could arise again, not from sunlight, but from the rhythm of the pulsar itself. It would be life without light. Creatures, if they existed, would navigate through vibration and magnetic sense. They might hear the spin of their sun like a heartbeat, constant, inescapable. To them, that pulse would not be death. It would be time itself. There's something hauntingly beautiful in that thought existence, born beneath a star that should have ended everything. The universe, it seems, refuses to stay still. Even after collapse, it finds new ways to breathe. Astronomers studying PSR B1257+ syndrome often describe it as a ghost system. Its planets are stable, but the light they orbit can never support life as we know it. And yet stability itself, the mere fact that orbits remain intact, that gravity still holds, is a form of survival. These worlds, dead or alive, are memory. They are monuments to endurance, proof that matter does not yield easily even to catastrophe. We can only imagine what their skies look like. From underground, through cracks in the rock, you might see flashes of blue and white scattered by dust refracted by the thin mineral atmosphere. Each flash would feel like lightning, silent and terrifying. There would be no stars beyond it, no constellations to follow, only the cold, rhythmic glare of the pulsar sweeping past. And yet in those flashes lies warmth, information, energy. The very radiation that kills also sustains the chemistry of possibility. Perhaps that is how the cosmos operates through contradiction. You can almost sense it now, the slow thrum of lightless oceans, the whisper of atoms rebuilding after ruin. The pulsar spins on unaware of what might cling to the shadows of its gravity. It does not nurture, but it does not forbid. As we rise away from these haunted worlds, the pulses grow dimmer, the intervals longer. The heartbeat fades into the hum of distant stars. Yet even in silence, one truth remains, that life, however fragile, has the audacity to exist wherever physics will allow. The pulse fades into background silence. We drift farther from the pulsar worlds, now away from their black skies and buried oceans, away from the rhythm of their deadly suns. And yet something about them lingers. It isn't their destruction that haunts us, but their persistence. Against all odds, against radiation, chaos and collapse, they remain. You and I are taught to see stability as safety as stillness. But in the universe, stability is often born from violence. The pulsar planets remind us that balance can exist not because conditions are gentle, but because extremes cancel each other perfectly. Radiation pushes, gravity pulls, motion fights decay, and somewhere between those opposing forces, order emerges. Let's look at the mathematics of it. Each pulsar planet moves in a dance of exquisite precision. If its orbit changed by even one part in a million, it would be flung into deep space or torn apart by tidal forces. Yet year after year, their orbits remain exact. The timing of their pulses, the tug of each planet on the pulsar repeats with microsecond perfection. Nature keeps time more faithfully than any machine we've built. That precision is not coincidence. It is the residue of catastrophe. When the system first formed, the chaos of debris and gravity left only those orbits capable of surviving endless radiation. Everything unstable was destroyed long ago. What remains now are only those paths that work. The universe, through trial and annihilation, carved perfection out of ruin. Perhaps stability then is not peace, but endurance. Imagine if life existed beneath the crust of one of these planets, feeding on residual heat or chemical energy. It would live inside a constant storm, adapting not to comfort but to the rhythm of disaster. Every pulse from the neutron star above would be a warning and a heartbeat. Life here would not evolve to escape danger, it would evolve to survive within it. That is the paradox: survival through tension, harmony through conflict. And it mirrors us more than we think. Earth too orbits within a narrow window of possibility. A few degrees closer to the sun and the oceans would boil. A few farther and they would freeze solid. Our planet, stable and peaceful to our eyes, is also a product of narrow balance, a thread of probability stretched across chaos. You can feel it, can't you? That quiet symmetry connecting distant worlds to our own. It's as if the same equation governs everything. Energy seeks equilibrium, even if the path toward it burns. The pulsar's radiation, Earth's sunlight, the magnetic storms of distant stars, all are expressions of the same universal law trying endlessly to balance itself. Maybe that's what these planets are telling us. That life and perhaps consciousness itself is not the triumph over chaos, but its continuation in another form. We are not separate from the collapse of stars. We are its slow echo given shape and voice. Look back once more at that dark system. The pulses still flash unseen, marking time for no one. The planets still orbit indifferent but precise. Their stability is their story, not because they are free from danger, but because they endure within it. Perhaps that is the ultimate lesson of physics, that everything stable is born from imbalance, everything eternal from decay. The universe, in its strange mercy, allows even destruction to find rhythm. And as we leave these ghost worlds behind, that rhythm follows us, the quiet ticking of the cosmos itself, reminding us that in a universe built from collapse, the most extraordinary thing is not chaos but continuity. The pulses that once marked the heartbeat of dead stars dissolve into a low hum, then into silence. As we drift away from the pulsar worlds, the darkness feels wider, softer, quieter, not the silence of death, but of distance. Those planets still circle their shattered suns, ticking like cosmic clocks, but from here they are only faint radio whispers rippling across the void. You can almost sense the change, a widening breath between worlds. After all, we've seen collapse, magnetism, radiation, the slow endurance of the impossible. There's something humbling about this calm, for in the end what saves us is not strength, not technology, not even understanding. It's distance, space itself. The emptiness between things is our greatest shield. psr J09520607. That monstrous neutron star spinning 700 times each second lies more than 14,000 light-years away. Its beams of radiation could vaporize an atmosphere, its magnetic field could erase every signal on Earth, but they can't reach us because the void is vast enough to dilute everything. Every threat the cosmos poses, every violent flash, every implosion, all are softened by the simple mercy of space. Imagine it each light-year as a wall of nothingness. Even light, the fastest thing we know, must spend millennia crossing that emptiness. Between every star, there are oceans of vacuum wide enough to swallow entire histories. We live safely not because the universe is kind, but because it is too large to notice us. That might sound lonely, but it's also grace. Our atmosphere, our quiet skies, our stable orbits exist only because we're far enough away from everything else trying to destroy itself. In this sense, space is not emptiness, it's insulation. The void is what keeps the fire from spreading. You and I can look up at night and see thousands of stars, each a sun, each surrounded by its own chaos. Yet none of them touch us. Their gravity tugs faintly, their light brushes our eyes, but their storms, their explosions, their deaths, all remain distant. And that distance is why we're here to see them. The cosmic microwave background, that ancient whisper of light from the birth of the universe, fills every direction. It is the oldest signal we can detect the residue of the Big Bang itself. Yet it too is a kind of refuge proof that everything violent eventually cools, stretches, and fades into peace. Space teaches us that survival isn't about power, it's about placement. A pulsar survives because it spins fast enough to resist collapse. A planet survives because it orbits in just the right corridor of stability. And we survive because our world sits in the narrow band between fire and ice, between the stars and the void. Our very existence is geometry, the outcome of perfect distance. Think of it this way: if Earth were just 1% closer to the Sun, its oceans would have boiled 1 billion years ago. If one magneta drifted within 50 light-years, its burst could have stripped our ozone in seconds. Every measurement, every kilometre, every degree is part of an invisible equation that keeps us safe. It's easy to think of distance as separation, as loneliness. But in the language of physics, distance is harmony. It allows motion without collision, energy without annihilation. It lets systems coexist, stars, planets, galaxies, all moving together yet apart. Distance is not the absence of connection. It is the reason connection lasts. You can almost feel it, the quiet comfort of being small in an endless sea. Every kilometre between us and disaster is a form of protection. Every empty region of space is a soft wall, a breath between heartbeats. So as we drift through this tranquil void, we begin to understand the paradox: emptiness. The very thing we fear is what saves us. It is the quiet barrier between life and catastrophe, between pulse and silence. The silence stretches like a horizon with no edge. We have drifted far from the magnetic storms, the dead suns, the flickering pulses of light. The emptiness feels calm now, almost kind. But it carries memory, the record of everything we've seen: stars crushed into spheres smaller than cities, light twisted into beams, gravity turned against itself. And in that memory lies a question: what exactly is the universe trying to teach us? Perhaps this is the lesson, that physics is not cruel, only complete. Every collapse, every burst, every annihilation obeys the same rules that allow atoms to form oceans, to stay liquid, hearts to beat. Destruction and creation are not opposites. They are phases of the same equation. Think of the neutron star we met first, psr J09520607, spinning faster than any mind can grasp. Its rotation, its density, its near collapse are all held in balance by the Pauli exclusion principle, by pressure between particles so small we can't see them. Inside that object, physics becomes prayer, simple, exact, absolute. Then the pulsar planets Drauga, Poltergeist, Phobetor, born from the dust of catastrophe. Their orbits are fragile but perfect. The same gravity that destroyed their parent star sculpted them into being. Chaos creates the geometry of survival. The magnetars, those titans of field and fury, reveal another truth: that strength without distance becomes annihilation. Their power bends, matter unravels, atoms erases the meaning of solid and liquid. But give that power space to expand a few dozen light-years, and it becomes harmless, even beautiful, painting the sky with soft radiation that fades into silence. Everywhere we look, the pattern repeats. In collapse we find structure, in destruction balance. In the smallest particles, the laws that hold entire galaxies steady. You and I often think of physics as something cold equations written in chalk, impersonal and remote. But what if it is more like rhythm, like music too vast to hear at once? Every neutron, every beam of light, every orbit is a note. Together they form the quiet harmony of existence. Maybe that's why the universe feels so immense it needs distance to let its laws breathe. If everything were closer, if stars collided, if fields overlapped, there would be no song, only noise. Distance again is not emptiness. It is time made visible, and perhaps that's where we come in. Our small world orbiting a calm yellow star is a tiny pocket of temporary order. The same physics that shapes neutron stars governs our rain, our clouds, our bones. We are made of matter that once endured those extremes. Every atom of iron in your blood was forged inside a collapsing star, the same kind of star whose remnants we've followed through this journey. So when we look at the night sky, we are not looking out. We are looking back at our origins written in magnetic storms and gravitational pressure, back at the conditions that made thought possible. Physics at its most extreme isn't trying to scare us, it's trying to remind us that we belong to the same law that bends space and burns stars, that we are not fragile exceptions but proof that order can rise out of fire, and that might be the quiet truth at the center of everything. The universe is not balanced because it is perfect. It is balanced because it never stops moving toward equilibrium destruction, feeding creation, collapsing back into silence. We are simply the moment in between the pause, between pulses, the breath between equations. The universe exhales. Silence returns, vast, infinite, patient. We float once more beneath a sky that seems unchanged, but everything we have witnessed lingers echoing quietly through the dark. All of it, the collapsing cores, the magnetic storms, the blackened worlds began as ordinary stars no different from our own sun. That is the final lesson and the final warning. Nothing in the cosmos stays safe forever. Even the sun, calm and familiar, will one day exhaust its fuel. Its light will swell, its atmosphere will peel away, and the orbits of our planets will falter. The calm we live within is not eternal. It is an interlude. The physics we have seen elsewhere, the violence, the collapse, the rebirth waits here too, hidden only by time. But time, like distance, is a fragile wall. We measure safety in centuries, but the universe measures it in millions of years. From its perspective, everything we know, every civilization, every language, every heartbeat, is only a flicker in the long rhythm of entropy. And yet there is peace in that. Because if we understand how fragile our place is, perhaps we will treasure it more. The blue glow of atmosphere, the balance of warmth and cold, the gentle pulse of a quiet star. We are temporary, but so is every danger. So let this be the final whisper of the cosmos. Watch the stars, but do not fear them. If stars can die twice, what does it mean to be stable at all? The question lingers in the quiet between galaxies. You can almost feel it, the faint pressure of a thought too vast to answer. Out here the stars no longer burn. They whisper. They cool, fade, and fold back into the fabric that once created them. What was once light becomes memory, and memory in turn becomes the raw material for new worlds yet to come. The universe runs on pressure and collapse, and our calm is the exception, not the rule. Every heartbeat of existence, every breath of creation is tension-seeking equilibrium. Gravity pulls, fusion pushes, and in that fragile balance, life finds a moment to exist. Our planet floats in that pause, not permanent, not protected, only balanced perfectly for now. Look up. Every star you see is already in motion toward its ending. Some will flare into supernovae, scattering carbon and iron into the dark. Others will shrink into white dwarfs, glowing faintly for billions of years before fading to black. A few, the restless, the massive, will spin themselves into collapse, becoming the singularities that swallow even light. And yet through every phase, every loss, the pattern remains. Matter transforms, never disappears. Death in the cosmos is not an ending, but a continuation by other means. You and I, we are proof of that law. The atoms in your skin were forged in stars that no longer exist. The oxygen you breathe was once trapped in a dying core. The iron in your blood carries the spectral signature of a long-extinguished sun. You are the echo of 1,000 collapses, the universe remembering itself in human form. Perhaps that's what stability truly means, not permanence but persistence. A willingness to endure through transformation, to remain recognizable even as everything changes. The stars have done this for billions of years. Now through you, the pattern continues. There's something almost merciful in that thought. We spend our lives searching for safety, for constants, for unchanging truths. But the universe offers none. What it offers instead is rhythm, the steady pulse of creation and decay. From the spin of electrons to the rotation of galaxies, everything moves in cycles, waves, oscillations. There is no stillness here, and that is why it lasts. Listen carefully and you can hear it, the slow hum of background radiation, the faint hiss of the cosmic microwave sky. It is not noise, it's memory, the sound of the universe cooling, expanding, breathing. Every photon in that whisper is 13.8 billion years old, carrying the signature of the first light stretched and softened by time until it became a lullaby. We are surrounded by that song even now. It seeps through every frequency, every silence between words. When you close your eyes, when the world grows still, that's what you're hearing. The fading afterglow of the beginning. The stars do not speak, but their silence tells you everything, that you are temporary yet connected to everything that has ever been. And maybe that's the paradox we were meant to find. If the stars can die twice, once in fire, once in memory, then perhaps we too live more than once. Not in body, but in the ripples we leave warmth, thought, motion, gravity. Every act, every breath, every photon we release joins that endless conversation. The cosmos does not forget. It only spreads what it learns. So when you look at the night sky, remember you're not watching light from distant suns. You're watching time itself arriving. You're seeing the universe as it was long before you, yet it's meeting you exactly where you are. Distance, delay, decay all working together to make the present possible. And in that delicate illusion of now, there is peace. Because the same forces that tear stars apart hold us together. Gravity, magnetism, the slow resistance of matter against collapse. The laws that shape destruction are the same ones that allow tenderness, balance, and thought. The calm of our world is not an accident. It's the brief alignment of impossible physics, a temporary kindness in a universe that owes us nothing. So let the silence of the stars remind you, there is no safety, only connection. No permanence, only rhythm. Every heartbeat, every orbit, every sigh of wind through atmosphere is a conversation between collapse and creation, between light and shadow time and entropy, you and the infinite. And as the last echoes fade, the universe begins to dim once more. Galaxies slide apart, the background cools, the stars go out one by one. Yet even then, even in the final darkness, the pattern remains the silent geometry of existence holding its breath. Tomorrow we travel where magnetism ends and darkness begins. There, beyond the last photon, beyond the reach of memory, we'll find not an ending, but a pause, a deeper kind of silence waiting to be understood.